Azlan Adnan, M.A. presents Navigating the Protein Paradox After 40, Building Strength Without Fueling Inflammation or Cancer Risk. How anabolic resistance changes the rules of muscle preservation, and the practical strategies that let adults over 40 hit higher protein targets without turning protein into a dietary obsession. Saturday, August 15, 2026. Dedication to Jaden Johnson, whose questions inspired me to explore this subject matter deeply. If you are over 40 and determined to remain strong, mobile, and metabolically healthy, you have probably encountered one of the more confusing nutritional questions of midlife. How much protein is enough to preserve muscle and bone without turning a potentially beneficial nutrient into another source of metabolic stress? The conventional answer is increasingly unsatisfactory. The old adult recommended dietary allowance of 0.8 grams of protein per kilogram of body weight per day was designed primarily to prevent deficiency. It was not designed around the more demanding objective of preserving muscle mass, strength, and physical function into the 7th, 8th, and 9th decades of life. Yet the opposite response, simply eating enormous quantities of protein, is not necessarily the answer either. Protein is biologically active. Amino acids do more than provide building blocks for muscle. They participate in signaling pathways that regulate growth, metabolism, insulin sensitivity, and cellular proliferation. Dietary protein can influence insulin-like growth factor 1, IGF-1, mechanistic target of rapamycin complex 1, mTORC1, glucagon, and other metabolic pathways. This creates a genuine paradox. Too little protein can contribute to frailty and sarcopenia. Too much protein, particularly when it comes predominantly from animal foods and replaces fiber-rich plant foods, may carry metabolic and possibly longevity costs. The solution is therefore not maximal protein. It is adequate, intelligently distributed, and physiologically appropriate protein, combined with resistance exercise, sufficient energy, sleep, metabolic health, and a predominantly whole food dietary pattern. The root cause, anabolic resistance. Beginning in midlife and becoming more pronounced with advancing age, skeletal muscle becomes less responsive to the anabolic or muscle building effects of dietary protein and exercise. This phenomenon is known as anabolic resistance. Think of muscle as a construction site. Protein supplies the raw materials, while resistance exercise supplies the instruction that construction is required. With age, the construction site becomes less responsive to both signals. More raw material may therefore be required to produce the same amount of construction. This does not mean that older muscle is incapable of responding. It means that the stimulus has to be sufficiently strong. Research indicates that older adults may require approximately 0.4 grams of high-quality protein per kilogram of body weight in a meal to maximally stimulate muscle protein synthesis under experimental conditions, compared with approximately 0.24 grams per kilogram in younger adults. For an 80-kilogram older person, that corresponds to roughly 32 grams of protein in a meal. Several physiological changes contribute. Older muscle appears to have a reduced sensitivity to amino acid signaling, including signaling through mTORC1, a cellular pathway that helps regulate protein synthesis. Older adults may also experience greater extraction of amino acids by the gut and liver before those amino acids reach peripheral tissues. Physical inactivity, insulin resistance, inflammation, illness, and inadequate energy intake can further compound the problem. The result is sarcopenia, the age-associated deterioration of skeletal muscle mass, strength, and physical performance. Sarcopenia is not merely cosmetic. Muscle is an organ of locomotion, glucose disposal, amino acid storage, and metabolic resilience. Losing it increases the risk of falls, disability, frailty, and loss of independence. But there is an important qualification. Age itself is not the whole explanation. Sedentary behavior, inadequate resistance exercise, excess visceral fat, chronic disease, insufficient energy intake, and poor nutrition can all contribute to the deterioration conventionally attributed to aging. Regular aerobic and resistance exercise can counter many aspects of age-related muscle decline, while adequate protein and energy intake provide nutritional support. In other words, anabolic resistance is real, but it is not a sentence. Why the 0.8 g per kilogram RDA is not the same as an optimal target. The distinction between an RDA and an optimal intake is crucial. An RDA is essentially a population-level threshold designed to prevent inadequacy. It should not automatically be interpreted as the quantity required to maximize muscle function in an older, physically active person. The PROTAGE study group concluded that adults over 65 generally require at least 1.0 to 1.2 grams per kilogram per day, with is greater than or equal to 1.2 grams per kilogram per day appropriate for older people who are physically active. For older adults with acute or chronic illness, 1.2 to 1.5 grams per kilogram per day may be appropriate, while considerably higher intakes may sometimes be used during severe illness, injury, or marked malnutrition. ESPEN similarly recommends at least 1.0 to 1.2 grams per kilogram per day for healthy older adults, with individualization according to nutritional status, physical activity, disease, and tolerance. This provides a more sensible framework than either extreme. 0.8 grams per kilogram is not necessarily an optimal target for an older active person, but neither is 2 to 3 grams per kilogram automatically better. For a healthy resistance training adult over 50, approximately 1.2 to 1.6 grams per kilogram per day is a reasonable practical range for consideration. Higher intakes may have a place during clinically significant catabolic stress, but they should not be presented as a universal longevity prescription. People with significant kidney disease require individual medical advice rather than generic high-protein recommendations. PROTAGE specifically identifies severe non-dialysis kidney disease as an important exception. The IGF-1, mTOR, inflammation and longevity paradox. Here the protein debate becomes much more interesting. Protein is not simply structural material. Amino acids also function as signals. One important pathway is mTORC1, mechanistic target of rapamycin complex 1. In simple terms, mTORC1 is part of the cell's nutrient-sensing machinery. When nutrients and growth signals are abundant, it helps tell cells that conditions are favorable for growth and protein synthesis. Another important system is growth hormone and IGF-1. IGF-1, or insulin-like growth factor 1, is essential. It supports normal growth, tissue repair, and many aspects of metabolism. The question is not whether IGF-1 is bad. It is whether chronically stimulating growth-promoting pathways beyond what is necessary is desirable throughout the entire human lifespan. This is where the work associated with T. Colin Campbell and other researchers enters the discussion. Campbell has argued that dietary protein, particularly certain animal proteins, can influence growth factor signaling and cancer biology. His work helped popularize the hypothesis that protein quantity and source can influence IGF-1 and other growth-related pathways. But this hypothesis needs to be handled carefully. It is scientifically unjustified to translate the mechanistic evidence into the statement that protein causes cancer, or that eating more protein automatically produces cancer. Cancer is a multifactorial disease involving genetics, accumulated mutations, immune surveillance, environmental exposures, body composition, hormones, inflammation, and many other factors. The strongest conclusion is considerably narrower. Protein intake and protein source can influence biological pathways associated with growth and metabolism, and these pathways are relevant to cancer biology. That does not establish that a particular protein intake causes cancer in an individual. This distinction matters. The famous protein mortality reversal, one of the most provocative findings in this field, came from the 2014 analysis by Morgan Levine, Valter Longo, and colleagues. In adults aged 50 to 65, high protein intake was associated with higher overall and cancer mortality, whereas these associations were attenuated when protein was predominantly plant-derived. After age 65, however, higher protein intake was associated with lower mortality. This produced a striking hypothesis. Protein restriction may be more favorable during middle age, whereas adequate or higher protein may become increasingly important in later life. The biological logic is plausible. During middle age, excessive stimulation of growth pathways may theoretically be less desirable, while in advanced age the immediate danger of losing muscle may outweigh the theoretical longevity advantage of maintaining lower protein intake. But this finding should not be treated as settled clinical law. A newer NHANES3 analysis published in 2025 reached a substantially different conclusion. It found no significant association between usual animal or plant protein intake and all-cause mortality, and no association between circulating IGF-1 and mortality. Its results did not reproduce the dramatic mortality associations reported in the earlier analysis. This is an excellent example of why nutritional epidemiology must be interpreted cautiously. Association is not causation, and apparently contradictory cohort studies are not unusual when diet, age, health status, lifestyle, and statistical modeling interact. The sensible conclusion is not that IGF-1 is irrelevant, nor is it that protein restriction prevents cancer. Rather, the evidence supports avoiding unnecessary excess while ensuring sufficient protein to preserve physical function. The inflammation connection. Aging is accompanied in many people by a persistent, low-grade inflammatory state sometimes called inflammaging. Inflammation is useful when the body needs to fight an infection or repair an injury. The problem arises when inflammatory signaling remains chronically elevated. Inflammation can interfere with muscle metabolism, promote insulin resistance, and accelerate protein breakdown. At the same time, insulin resistance and physical inactivity can make muscle less responsive to anabolic signals. This creates a vicious cycle. Inactivity, right pointing arrow insulin resistance, right pointing arrow inflammation, right pointing arrow anabolic resistance, right pointing arrow muscle loss, right pointing arrow reduced activity. Breaking the cycle therefore requires more than adding protein powder. It requires making muscle metabolically receptive to protein again. And the most powerful tool for doing that is not another supplement. It is resistance exercise. Resistance training is the missing half of the protein equation. A protein-rich meal without a reason for the muscle to adapt is not the same thing as a protein-rich meal following mechanical loading. Resistance exercise tells muscle, we need to become stronger. Dietary amino acids then provide the raw materials. This is why the protein question should never be separated from exercise. For an adult over 50, 2 or 3 well-designed resistance sessions per week can be enormously more consequential than obsessing over whether lunch contained 27 or 31 grams of protein. The target is progressive overload, gradually asking the muscles to perform more work, whether through heavier weights, greater resistance, more repetitions, better control, or more demanding movements. Muscle responds to challenge. Protein supports the response. Leucine, the amino acid that rings the alarm bell. Protein quality is not merely about the number of grams printed on a nutrition label. Proteins contain amino acids, including 9 essential amino acids that humans cannot manufacture in sufficient quantities and therefore must obtain from food. One of these is leucine. Leucine acts partly as a nutritional signal that helps activate the machinery involved in muscle protein synthesis. In older adults, approximately 2.5 grams or more of leucine per meal is often discussed as a useful target for overcoming anabolic resistance, although there is no universally agreed leucine threshold that applies identically to every person. This is one reason a 20g protein meal and a 30g protein meal cannot necessarily be considered biologically identical. It also explains why plant proteins sometimes require somewhat larger quantities. But this does not mean that plant protein is incomplete. Christopher Gardner of Stanford has been particularly vocal about this misconception. Plant foods contain all 20 amino acids. The issue is their relative proportions and digestibility, not the complete absence of particular amino acids. The old instruction to combine beans and rice at precisely the same meal to create a complete protein is therefore unnecessarily rigid. Eating a varied diet over the course of the day is sufficient for most people. Plant protein is not a second-class protein. Plant proteins can differ from animal proteins in amino acid composition, digestibility, and leucine density. That is a biochemical reality. But biochemical differences should not be confused with clinical inferiority. A 2024 randomized crossover trial involving 34 adults averaging 72 years of age found that a varied vegan diet providing the same energy and nitrogen as an omnivorous diet did not compromise daily mixed muscle protein synthesis. An additional 2025 randomized trial in adults aged 50 to 70 compared an animal-focused whey-supplemented diet with a plant-focused pea protein diet, both providing 1.0 grams per kilogram/day. Resistance training increased muscle protein synthesis in the trained limb, with no difference between the protein source groups in daily myofibrillar protein synthesis. These studies do not prove that every plant protein behaves identically to every animal protein. They demonstrate something more useful. A well-designed plant-based diet can provide sufficient anabolic stimulus when total protein, amino acid availability, and exercise are adequate. Soy is particularly useful because its amino acid profile and leucine content are relatively favorable among plant foods. Tofu, tempeh, edamame, soy milk, and other minimally processed soy foods can therefore be valuable components of an older person's protein strategy. Legumes, peas, lentils, beans, whole grains, nuts, and seeds provide additional protein while simultaneously delivering fiber, potassium, magnesium, polyphenols, and other compounds that are largely absent from isolated animal protein. Christopher Gardner's protein lesson: change the food, not just the macronutrient. Christopher Gardner's contribution to this discussion is important because he challenges the tendency to treat protein as an isolated nutrient. The question is not simply, where can I get more protein? It should also be, what food comes packaged with that protein? A serving of beans delivers protein together with fiber and a wide spectrum of micronutrients and phytochemicals. A serving of nuts delivers protein with unsaturated fats and minerals. Soy provides protein alongside other bioactive compounds. Conversely, a protein-rich food can arrive with substantial saturated fat, sodium, or other dietary components depending upon its source and processing. Gardner and colleagues have argued for shifting part of dietary protein consumption from animal to plant sources, rather than treating animal protein as nutritionally indispensable. Gardner's broader point is particularly valuable. Protein quality should ultimately be judged by the health consequences of the food providing it, not merely by its amino acid score. Cyrus Kambata and the insulin sensitivity argument. Cyrus Kambata, PhD, approaches the protein question from a different but complementary direction. His Mastering Diabetes framework emphasizes whole food, plant-based, low-fat nutrition, physical activity, and improving insulin sensitivity. Kambata argues that very high-protein diets can be problematic for metabolic health, and places considerably greater emphasis on carbohydrate-rich whole plant foods than many contemporary high-protein diets do. The important concept here is metabolic context. Insulin resistance means that cells become less responsive to insulin signal. In skeletal muscle, this can interfere with the normal handling of glucose and nutrients. Kambata's argument is that treating protein as the universal solution to metabolic dysfunction can obscure the larger dietary pattern. Replacing carbohydrate-rich whole plant foods with large quantities of protein and fat may not necessarily improve metabolic health, particularly when the diet becomes energy-dense and fiber-poor. His position is more restrictive than the mainstream protein recommendations for older adults, and some of his broader therapeutic claims should not be treated as established consensus. Nevertheless, his emphasis on insulin sensitivity makes an important contribution to the protein debate. The objective is not merely to feed muscle. It is to maintain a body in which muscle can efficiently use the nutrients being supplied. Michael Greger and the protein supplementation question. Michael Greger, MD, takes the skeptical side of the protein debate considerably further. Greger has highlighted randomized trials in older adults in which increasing protein intake did not produce the dramatic improvements in muscle mass, strength, or performance that might be expected from the popular high-protein narrative. This is an important corrective. If an older person already consumes an adequate diet and then adds large quantities of protein powder, the additional protein does not automatically become additional muscle. Greger's position is particularly strong on the primacy of resistance exercise. His interpretation of the intervention literature is that exercise itself is much more consistently associated with improvements in muscle strength and function than simply adding protein. That does not mean protein is irrelevant. It means that protein cannot substitute for mechanical loading. Nor does it justify allowing an older person to consume inadequate protein. The correct interpretation is more nuanced. Once protein adequacy has been achieved, progressively increasing protein may produce diminishing returns, and the marginal benefit of another scoop of powder may be considerably smaller than the benefit of another properly performed resistance training session. The protein paradox is therefore not really a paradox. Once the evidence is assembled, the apparent contradiction becomes easier to understand. The body has two competing biological imperatives. One is growth and repair. The other is long-term maintenance and protection against excessive growth signaling. During youth, growth signaling is advantageous. During old age, maintaining muscle and functional capacity becomes increasingly important. Between these two extremes lies midlife, when excessive growth signaling may theoretically be less desirable, but muscle preservation is already becoming increasingly important. This produces a moving target. Protein requirements are therefore not a single number carved permanently into human physiology. They are influenced by age plus body composition plus physical activity plus resistance training plus energy intake plus protein quality plus health status plus metabolic health. How much protein should an adult over 50 actually eat? For a healthy adult over 50, a practical starting point is approximately 1.2 to 1.6 grams per kilogram per day, particularly when resistance training regularly. This is not a universal prescription. A sedentary individual with a healthy body composition may not need the upper end. A physically active person attempting to preserve or rebuild muscle may benefit from it. During acute illness, injury, or severe catabolic stress, clinical requirements may be higher. Conversely, people with significant renal disease require individualized medical advice. For someone weighing 70 kilograms, 1.2 to 1.6 grams per kilogram corresponds to approximately 84 to 112 grams of protein per day. But body weight itself is not sacred. In people with substantial obesity, using goal body weight or an adjusted body weight may sometimes be more rational than multiplying total body weight by a high protein target. The important point is that the target should be physiologically justified rather than ideologically inflated. Distribution may matter more than you think. Eating nearly all of one's protein at dinner is probably less efficient for muscle maintenance than distributing meaningful protein doses across the day. For many older adults, approximately 25 to 40 grams of protein at each of 3 meals is a practical framework, adjusted for body size and the protein source. Breakfast deserves particular attention. A common Western eating pattern provides relatively little protein in the morning, modest amounts at lunch, and a large quantity at dinner. For an aging muscle, spreading the stimulus more evenly makes physiological sense. The objective is not mathematical perfection. It is to avoid spending the entire day below the threshold needed to stimulate muscle protein synthesis, and then attempting to compensate with one enormous evening meal. Plant-based protein, a smarter way to reach the target. A plant-forward protein strategy can be built around tofu and tempeh, edamame and other soy foods, lentils, chickpeas and beans, peas, seitan where gluten is tolerated, quinoa and other protein-containing whole grains, nuts and seeds, and, when useful, appropriately formulated plant protein powders. There is no physiological requirement to combine complementary proteins at every meal. Variety across the day accomplishes what is required. For people relying heavily on plant protein, however, a slightly larger protein serving can be useful because many plant foods have lower protein density and, in some cases, lower digestibility or leucine concentration than animal proteins. This is a quantitative adjustment, not an admission of nutritional inferiority. The case for protein diversity. One of the most sensible approaches is to avoid making any single protein source the center of the diet. Instead, think in terms of a protein portfolio. Soy provides a high-quality plant protein. Legumes provide protein plus fiber. Whole grains contribute additional amino acids and energy. Nuts and seeds contribute protein together with unsaturated fats and minerals. Vegetables and other plant foods contribute smaller quantities that accumulate over the day. This approach also fits Gardner's broader argument that nutrition should be evaluated at the level of dietary patterns rather than isolated nutrients. What about meat, eggs, and dairy? The evidence does not support the simplistic claim that every gram of animal protein is harmful, nor does it support the opposite claim that animal protein is inherently superior for healthy aging. Some animal proteins are highly digestible and rich in essential amino acids, including leucine. They can therefore be efficient tools for meeting protein requirements. The question is what they displace. Replacing beans, lentils, whole grains, vegetables, nuts, or soy with large quantities of processed meat is not nutritionally equivalent to adding a modest amount of fish or yogurt to an otherwise plant-rich diet. Large observational studies have repeatedly found more favorable mortality associations for plant protein than animal protein, particularly when plant protein replaces processed or red meat. But more recent NHA-NES analysis illustrates that the evidence is not uniform and that sweeping claims about animal protein causing mortality are not justified. The prudent conclusion is, therefore, prioritize plant protein, minimize processed meat, treat red meat as an occasional rather than foundational protein source, and judge animal foods within the context of the entire dietary pattern. Protein, information, and the Mediterranean plant-focused pattern. Protein should not be considered independently of the foods surrounding it. A high-protein diet based on processed meat, refined carbohydrates, and ultra-processed foods is metabolically different from a diet containing similar protein but built around legumes, soy, vegetables, fruits, whole grains, nuts, and seeds. The latter provides fiber and numerous phytochemicals that influence the gut microbiome, glucose metabolism, and inflammatory signaling. This is why a plant-forward dietary pattern can solve several problems simultaneously. It supplies protein. It supplies fiber. It increases micronutrient density. It reduces the need to obtain protein from heavily processed foods. And it allows protein intake to rise without necessarily requiring a corresponding increase in animal food consumption. Omega-3, creatine, and other supporting factors. Protein is only one component of the muscle preservation equation. Omega-3 fatty acids may influence muscle metabolism and inflammatory signaling, although the evidence is not strong enough to justify treating very high-dose omega-3 supplementation as mandatory for everyone. Creatine is more interesting. Creatine is stored primarily in skeletal muscle and helps regenerate adenosine triphosphate, the immediate energy currency used during short bursts of muscular effort. Supplementation has reasonably strong evidence for improving strength and lean mass when combined with resistance training, including in older adults. A common supplemental dose is 3 to 5 grams per day of creatine monohydrate. This is fundamentally different from taking a large quantity of protein powder. Creatine is not a protein source. It is a compound involved in cellular energy metabolism, vitamin D status, adequate calcium, sufficient energy intake, and sleep also matter. Muscle cannot be built efficiently when the body is chronically underfueled. Sleep is part of the protein equation. Muscle repair does not occur merely because amino acids entered the bloodstream. Recovery requires adequate sleep. Chronic sleep restriction alters endocrine function, appetite regulation, glucose metabolism, and recovery from exercise. It can therefore undermine the very adaptation that a high-protein diet is intended to support. For most adults, approximately 7 to 9 hours of good quality sleep remains a sensible target. Protein cannot compensate indefinitely for inadequate recovery. Visceral fat is the hidden opponent. There is another reason protein alone cannot solve the problem of age-related muscle loss. Sarcopenia and obesity can coexist. This condition is sometimes called sarcopenic obesity. An individual can carry substantial fat mass while simultaneously losing functional muscle. Visceral adipose tissue is metabolically active. Excess visceral fat is associated with insulin resistance and inflammatory signaling, creating an environment in which muscle becomes less responsive to anabolic stimuli. Thus, improving body composition can make the protein one eats more effective. The objective should not simply be a lower number on the bathroom scale. It should be more functional lean tissue and less metabolically harmful fat. A more intelligent protein framework for adults over 40. The practical solution can therefore be reduced to a few principles. First, establish adequacy rather than chasing excess. For many healthy active adults over 50, 1.2 to 1.6 grams per kilogram per day is a reasonable working range. Second, distribute protein. 3 substantial protein-containing meals are generally more sensible than consuming almost everything at night. Third, pay attention to leucine without becoming obsessed with it. Protein-rich soy, legumes, and other plant foods can be consumed in sufficient quantities to provide substantial essential amino acids. Protein isolates can be useful when food volume becomes impractical. Fourth, lift something. Resistance training is the principal physiological signal telling muscle that it must remain. Fifth, improve insulin sensitivity. Regular exercise, healthy body composition, adequate sleep, and a fiber-rich dietary pattern can make muscle more metabolically responsive. Sixth, make plants the foundation rather than treating them as decoration. Protein should arrive packaged with fiber, micronutrients, and phytochemicals whenever possible. Seventh, be cautious about the longevity claims surrounding IGF-1. IGF-1 is biologically important, and protein growth signaling is a legitimate area of aging research. But the evidence does not justify claiming that a particular amount of protein will prevent or cause cancer. Eighth, distinguish muscle preservation from bodybuilding. The goal for most adults over 50 is not to maximize muscle hypertrophy. It is to maintain enough muscle strength, power, and function to remain independent. That is a very different target. The deeper lesson from Campbell, Gardner, Kambata, and Greger. The most useful insight emerges not from choosing one expert and rejecting the others, but from understanding what each perspective contributes. Campbell reminds us that protein is a biologically active signal, and that growth factor pathways deserve consideration when thinking about long-term health. Gardner reminds us that protein should be evaluated as part of a food and dietary pattern, and that plant proteins are perfectly capable of supporting human nutrition without the mythology of incomplete proteins. Kambata reminds us that insulin sensitivity and metabolic health matter, and that simply adding protein can distract from the importance of whole plant foods, physical activity, and overall dietary composition. Greger reminds us to demand actual intervention evidence before assuming that more protein automatically produces more muscle, and to keep resistance exercise at the center of the discussion. The geriatric nutrition literature adds another essential piece. Older adults genuinely do require attention to protein adequacy, and expert groups such as Protage and ESPEN recommend intakes above the conventional 0.8 grams per kilogram RDA for many older people. These propositions are not mutually exclusive. They fit together. The goal is effective protein, not maximum protein. The modern protein debate has been distorted by an understandable but dangerous equation. More protein equals more muscle equals better health. Human physiology is more complicated. Protein is necessary, but more is not automatically better. The relevant question is whether the amount consumed is sufficient to overcome anabolic resistance, whether it is distributed effectively, whether the essential amino acids are available, whether the person is providing the muscle with an appropriate training stimulus, and whether the surrounding dietary pattern supports metabolic health. This is why the concept of effective protein is more useful than the concept of maximal protein. Effective protein is protein that the body can use productively. It is consumed in an appropriate quantity. It arrives with an adequate amino acid profile. It is distributed across the day. It is accompanied by resistance training. It exists within a diet that supplies sufficient energy, fiber, micronutrients, and phytochemicals. And it does not require sacrificing long-term dietary quality simply to achieve a number on a protein calculator. The final balance. There is no need to choose between muscle and longevity. The apparent conflict becomes much less formidable once protein is placed in its proper physiological context. After 40, and especially after 50 or 60, the objective should be to raise protein adequacy modestly while raising exercise quality substantially. For many people, that means moving from approximately 0.8 grams per kilogram toward 1.2 to 1.6 grams per kilogram per day rather than leaping immediately to extreme intakes. It means eating meaningful protein at breakfast and lunch instead of reserving most of it for dinner. It means using legumes and soy more deliberately. It means treating leucine as a useful physiological concept rather than a marketing slogan. It means lifting weights. It means sleeping. It means reducing visceral fat and improving insulin sensitivity. It means recognizing that a gram of protein from a lentil is nutritionally different from a gram of protein arriving inside a processed meat product, even though the amino acid molecule itself is ultimately the same building material. And it means acknowledging the limits of the evidence. The claim that too little protein is dangerous is well supported in the context of aging, frailty, and inadequate nutrition. The claim that more and more protein is necessarily better is not. The claim that animal protein inevitably causes cancer through IGF-1 is also not established. The more defensible conclusion lies between these extremes. As we age, we should become more deliberate about protein, not more obsessive about it. The winning strategy is neither protein restriction nor protein maximalism. It is adequacy, distribution, quality, resistance exercise, and metabolic health. The ultimate objective is not to build the largest possible muscles. It is to arrive at old age with enough muscle, strength, and metabolic resilience that the body remains capable of carrying the life the mind still wants to live. Stay strong.
The author has placed this work in the public domain. It may be freely imported, exported, shared, distributed, edited, modified, or reformatted without explicit consent from the author. As a visually impaired person, the author asserts his rights under the Marrakesh Treaty to facilitate access to published works for persons who are blind, visually impaired, or otherwise print disabled. 2013, wipo.int.
Share your thoughts in the comments below. Don't forget to like this video and subscribe to our channel to show your support.